All right, guys, good day. So this is going to be the tutorial for the Atwood machine laboratory, which you can find in modules after the projectile motion lab. So you should have finished the projectile motion lab by now when you're watching this video. The force table, of course, the acceleration of gravity, projectile motion, and then you have the Newton's laws Atwood machine. Keep in mind that there is another lab after this, the incline plane. I will be uploading a video for that separately. This lab in particular, you are going to be using another software, another simulation, which is this one. Now, I opened the file here, and I saw that it might be difficult to click, but you can copy this website, and then basically it will give you this. So the idea with this is to simulate an Atwood machine, which is a device where two masses are connected by a pulley and where we neglect torque and any sort of friction. If you do that, you can find the acceleration of the system and the tension on the string. The idea is to do two experiments or two situations. On the first one, you are going to be having the total mass M1 plus M2 constant. And then you are going to be changing M1 and M2 5 times, and you're going to get an experimental acceleration. The experimental acceleration comes from here, of course, there. The theoretical acceleration comes from that equation, which is in the manual. M1 minus M2 times gravity divided by the sum of the masses. You are keeping the sum of the masses total because the force is equal to M1 minus M2 times gravity. So clearly, if you plot force versus, so this is table 1, if you plot force net versus acceleration, you should know what the slope will be. That's one of the questions here. Now, the way you're going to fill in this table is basically by, well, you can start with 1.2 and 1. The total mass here is 2.2 kilograms. So in Excel, by the way, the file for this Excel file is here. All right, down at the bottom of the Atwood machine doc experiment, which is this file. M1, M2, so you are going to vary. And for that, I'm just going to place the simulation a little bit where is it? Here. So if you play the simulation, that will happen. So this value will be the acceleration experimental, 1.2 and 1. So 1.2, 1, 2.2, of course, and this is 0.81. For this one, you want to add. You want to keep the total mass constant, so you want to add maybe 0.1 of a kilogram here and subtract it here. So that means that you have 0.2 still, at 1.2 still as total mass. So this will be 2.2 regardless. There. And you want to center this. And this will be 1.3, 1.4, 1.5, 1.6. And this will be 0.9, 0.8, 0.7, 0.6. And then here you will have the experiment. So to find that, you need to do the experiment, right? So 1.3 and 9, if you play, it's 1.82. And then you can reset this. And then you add, so 1.82 will go here. And then on 3, you will do 1.4 and 0.8. If you play 2.73. So you can see what I'm doing, right? That theoretical acceleration will be the formula, which is in the manual. m1 minus m2 times gravity divided by total mass here. So here you will do, you can do the equation here, by the way. You can do m1 minus m2 all in parentheses times 9 point, oh, this is what happens sometimes, 9.8. Then another parenthesis, you probably don't need them, but just in case, all divided by the sum of the mass, which you can just put 2.2. So close as you expect. And then you can bring this down and it should give you all the accelerations. All right. So there you are, very nice. The numbers are close. What about the force net? That's m1 minus m2 times gravity. So this will basically be m1 minus m2, parentheses, both of these, of course, times gravity. So you need this because you're going to plot the force. This one, just make sure you write them from the software. To be honest, you don't need like do any calculations. You can just go here and, write these values. And then the percentage difference will be the percentage difference between these two. So they will give you a list. So if you want to find this one, for example, it will be parentheses, the accepted minus the theoretical, divided by the accepted, and all in parentheses, of course, multiply by 100%. So yeah, well, of course, you have to take the absolute value of this, right? But so 2.14 difference, and then you can do that for like all of them, right? Now, it will probably be the same. This one, because we don't have values here, I didn't calculate, I didn't do this. But you have the idea. So that's how you fill the table. So then you're going to plot this by the acceleration. So the acceleration is experimental. All right. If I were to complete this with 1.5 and 0.7, 3.64, 1.6 and 0.6, 4.55. So then you are going to plot in this versus the x and y. This should be in the y axis. And there you have it. Okay? It's a linear trend. And I'm going to let you guys analyze what's the slope and what does it mean. Okay? And don't forget you have to do a percentage difference as well between the slope and the expected value. So think about what you are plotting. Force versus acceleration. Don't forget to add a title, and this should be bigger. So I will say you have to add axis titles, the trend line, you do it like this here, and then you do linear. More options to add the equation and R square value as the lab. So that's how it should look. So I'm pretty sure you can clearly tell what the slope should be. All right. So that's part one. It's pretty easy. Part two is very similar, but now you're going to have this value and you're going to plot acceleration versus 1 over the total mass. Because the slope will give you the other. And think about it. In here, you're going to keep going to have a constant total force. That means that M1 and M2, the difference should be the same. This can be done by adding the same mass to each side once you decide the difference. So yeah, I mean, the way you will do this, if you were doing this in a lab, the way you will do this in the simulation is by starting maybe at 0.4 and at 0.2 here. And then you want to keep adding, right? So here, the acceleration is 3.33, 0.4, 0.2. So the difference is 0.2. So 0.4, 0.2, 0.6. And then here, 0.5, 0.3, again 0.2, but it's 0.5, so 0.5, 0.3. This will be different now but the difference is 0.2. That's going to be important for this. So here will be 0.6, 0.4, 0.7, 0.5, 0.8, 0.6. So you do the experiment. I'm not going to complete this table because that's giving you too much, but that's basically what you could do. You could do this 0.5, 0.1 if you want. Try not to give the difference too large though, okay? Here is 1 over equals to 1 over parentheses this value, and then there you are. So that makes sense. The experimental acceleration is the same as before. It's equal to the subtraction of the masses. So parentheses m1 minus m2 times gravity divided by the total mass. Now the total mass it changes now. So that's why acceleration is going to be like that now. Now, the theoretical acceleration, oh wait, sorry, this should go here. This is a theoretical. Experimental we didn't see it, right? So let's go with 0.4.2. 0.4.2 give us 3.33. Yes, of course, makes sense. So very close. The net force, that's going to be constant now because that's now equals to the difference, which you can write 0.2 only, times gravity. That's always going to be the same no matter what. So you can just copy this all the way here. And then this comes from the simulator, and then you're going to plot acceleration experimental. Oh, sorry, that's bad. Acceleration experimental versus 1 over the sum of the masses. And that's it. That will be your data and some of your calculations. And then you just have to answer some of these questions. That's it for the lab. Okay. If you have any questions, as always, I'll be doing office hours, but it's not that complicated. I'm pretty sure everybody can get a hang of this. It's a rest from using exploration physics. This is a very useful one. Probably we will be using another one like this later on, okay? So I hope this is clear. And remember, don't miss the deadlines, okay? I can always extend the labs. I know it's an online course, but make sure you don't miss those deadlines because I try to keep so it's aligned with what you are doing in the lecture. So once you do the lecture on forces, tension, Newton's second law, applications of Newton's second law, then this lab will make sense. All right. Okay. So I'll see you guys for the next tutorial, which will be the incline plane.